Hi everybody, this is my presentation for Lab 2, which looks at the physics behind the motion of a falling object. The purpose of this lab was to observe the motion of a falling object that is dropped from rest and falls slowly straight down. This observational data was then compared to two computational models. The first model used the momentum principle and considered the effects of the gravitational force acting on the object. The second computational model was also based on the momentum principle and looked at the combined gravitational and drag forces acting on the object. The results from the experiment found that the model that includes the effects of gravity and drag on the object was more accurate than the model that just considers F-grav alone. The physics principles behind this lab were Newton's second law and drag. Newton's second law, as seen in the form below, is derived from the momentum principle, where the final velocity is equal to the initial velocity plus the net force divided by the mass multiplied by the change in time. In this experiment, the velocity is not constant because the net force is non-zero. We have two forces acting on the object, the gravitational force and the drag force. The velocity is then used in the position update equation to update the position of the falling object. This then repeats with the final velocity being used as the initial velocity and the final position being used as the initial position to iterate through for the set period of time. The net force is calculated by adding together all the forces acting on the object. In this case, that would be the gravitational force, also known as weight, and the drag force. F-grav is found by multiplying the mass of the object times the gravitational constant times the unit vector j hat. The drag force is the force acting on the object in the opposite direction to its velocity. It's found by multiplying a proportionality constant b by the square of the velocity. This is a clip of my observational data. The experiment setup was as follows. The mass of the paper ball was 0.0023 kilograms. The reference length was the light switch, and it was 0.121 meters. The video's frame rate was 30 frames per second. The axis was oriented so the positive y direction was facing up. Since the object was starting from rest, the initial position and initial velocity were both 0. All of this information was input into the tracker application for data analysis. As you can see here, the observational data was analyzed in Tracker. The top right graph demonstrates the graph for the time versus y position of the falling object. The object is not moving with a constant velocity, which is why the graph curves and is not in a straight line. This series of images demonstrates the Python code for the computational model of the gravitational force. The ball's mass was updated and the position and velocity vectors were initialized to 0. The delta t time step was kept small so that the data collected was accurate. The j-hat vector reflected the axis chosen. The time was updated to reflect the length of the video, and the calculation for the weight force was added in. In this model, F-grav was the only force acting on the object, which is why F-net equals W in the code. The velocity equation and position equation were also updated to reflect Newton's second law. After the code was run, the results looked like this. When we compare the observational data to the model of the gravitational force, we get a graph that looks like the one on the left. As you can see, the model overestimates the effect of the weight force on the object, so there has to be another force acting on the object in order to make it act like the data we observed. This is the drag force. The unevenness of the observational data could be a result of movement in the x direction, meaning the object didn't fall completely straight down. The following images demonstrate the Python code for the combined weight and drag forces. In this case, everything was left the same except for the proportionality constant, which was found by a process of trial and error by changing the constant until the output y position value from the model was matched to the output y position from the observational data. Then in the while loop, the code was updated to reflect the drag force equation, which is negative b times the magnitude of the velocity squared times negative j hat. The net force was then updated so that it was found by adding the weight force and the drag force together. The final changes were in the bottom part of the code, where the forces were represented by arrows on the Python code. The arrow scale was found by dividing 2 meters by the magnitude of the gravitational force to determine how long to draw the arrows to represent the vectors. This is the result from the Python code. The final bit of data analysis compares both models to the observational data. As we can see here, our model that predicts the position using both the weight and drag forces is much more accurate than the model that predicts the position based on just the weight force alone. However, we used our observational data to fit the drag model, so the final position isn't actually a predicted position. Instead, the middle of the graph, from approximately 0.1 seconds to 0.6 seconds, is the predicted output, and this demonstrates that the drag model still overpredicted the position. Overall, the model that includes both the gravitational force and the drag force is the best predictor of the object's position. To answer the first question, the drag force model predicts terminal velocity. Terminal velocity occurs when an object reaches a certain speed where the drag force on the object is equal to the gravitational force on the object, which leads to the object moving with a constant speed and no acceleration. This can be seen in the graph below at approximately 0.6 seconds. The object's position is changing at a constant rate, which is indicative of a constant velocity, meaning the object reaches terminal velocity or freefall in this model. This is demonstrated by the red square shown in the graph. To answer the second question, if the object was thrown with an initial velocity, the terminal velocity would occur faster than if the object was dropped from rest. The head of the arrow demonstrates the point at which the object begins to move at a constant rate, and this is earlier than if the object was dropped from rest. The object would also be predicted to drop further.